Okay guys, in this video we are going to be talking about covalent bonds. Covalent bonds are what hold molecules together, and instead of what we had with the ionic compounds, where we could think of the bond as involving a transfer of electrons from the cation to the anion, covalent bonds involve a sharing of electrons between atoms. And that's what the co in covalent bonding means. It means that we have valence electrons that are shared between two atoms. And in the early days of quantum mechanics, it was shown that, that this is what gives rise to the stability of simple molecules, like, for example, a diatomic H2 molecule. And what you need in order to form a covalent bond is you need an overlap of the atomic orbitals that make up the molecule. This is what allows electron density to be shared between two atoms. So one of the criterion for forming a covalent bond is that you have overlap of the atomic orbitals of the two atoms that make up the bond. And so in the molecule, you're going to have all sorts of interactions. You're going to have repulsive interactions between the two nuclei. You'll have attractive interactions between the electrons and the nuclei. And you'll also have electron-electron repulsive interactions. Okay, so there's electrostatic interactions within a molecule. And then there's another type of interaction called the exchange interaction, which is a quantum mechanical effect that results in attraction between two atoms. And it turns out that it's this exchange interaction that is primarily responsible for the stability of molecules. It's a purely quantum mechanical effect that you don't actually observe in macroscopic matter. So this is unique to microscopic molecules. Here's a diagram depicting the energy change when you stretch a covalent bond. So this is diatomic hydrogen. If you put the atoms too close together, the repulsive interactions between the nuclei will be very strong. However, as you expand the molecule, that is, if you make the distance between the two atoms longer and longer, you see that the energy drops. Okay? It bottoms out at a certain point, and that's what we call the bond length of the molecule at this particular distance. And then as you continue to stretch the bond, that is, if you bring the atoms farther and farther apart, you see that the energy more gradually relaxes to zero. Okay? And so out here, the atoms are completely separated from one another, and so there's no interaction between them. As they get closer and closer together, okay, you have attractive interactions and exchange interactions turning on that cause the energy to go down. Okay? It goes through a minimum, and then if you start pushing the two nuclei closer and closer together, then you're going to have repulsive interactions kick in, and then the energy rises dramatically and goes up. Okay? And so this is the typical profile for a covalent bond. Okay? It's repulsive at short distances, it's near zero at large distances, and then it goes through a minimum at some intermediate distance. What I wanted to point out here, this is where you find the stable chemical bond in this region. And in order to break that bond, in order to separate the two atoms, you have to put energy into the molecule so that the energy goes up. So bond breaking is always an endothermic process. And when you take separated atoms and form a bond, it's always an exothermic process. This is sometimes a confusing point for general chemistry students because we often use the statement that there's energy stored within chemical bonds. Right? That's a common thing to hear colloquially. And it's something of a misnomer because it implies that if there's energy stored within a chemical bond and you break the chemical bond, then that's going to release the energy. But the situation is actually the opposite of that. Okay? In order to break a chemical bond, you have to put energy in. When bonds form, then energy is released. And so chemical energy comes from breaking weak bonds and forming stronger bonds. Okay, it's that forming the stronger bonds is what releases energy. So keep this in mind. This is a very important conceptual point that's often misunderstood. Bond breaking is endothermic, bond forming is exothermic. Well, these covalent bonds that we're talking about, the electrons are being shared between two atoms in a molecule. However, the electrons are usually not equally shared between two atoms. For the case of homonuclear diatoms, okay, where the two atoms that are bonded together are the same, as in H2O2, diatomic chlorine, in homonuclear diatoms, the electrons are evenly shared between the two atoms, and we say that the molecule is nonpolar. However, for heteronuclear diatoms, the electrons will typically not be equally shared, and then that is going to give rise to what we call a polar bond and a polar molecule. And so a good example of that is hydrogen chloride. So this sphere over here represents the hydrogen atom. This one represents the chlorine atom. In hydrogen chloride, chlorine tends to draw the electrons toward itself more so than the hydrogen can. Okay? So chlorine is going to take on a partial, that's what this little delta means, a partial negative charge, whereas the hydrogen atom is going to have a partial positive charge. We say that the chlorine side of the molecule is the electronegative side, whereas the hydrogen is the electropositive side. Okay? This difference in the ability to attract electrons to a given atom gives rise to what we call a polarity. And so this arrow here represents what's called a dipole moment. Okay? Since the chlorine side of the molecule tends to have more electrons around it than the positive side, it takes on a negative character. The hydrogen side is a little bit more positive. Whenever you have an unequal sharing of the electrons in a chemical bond, we say that there is a dipole moment in the molecule, and so the molecule has a negative end and a positive end. And that's depicted by this arrow here, where you draw a plus sign on the positive side of the molecule, pointing to the negative side of the molecule. We call this the dipole moment, and this is a polar molecule. The polarity of a given molecule increases with the difference in metallic character between the two atoms. And so hydrogen is much more like a metal than chlorine is. And so this gives rise to a polar bond. We use the term electronegativity to quantify the ability of an atom in a molecule to pull electrons towards itself. There's various ways of defining electronegativity. One is called the Mulliken approach, the Mulliken scale, and it's based on a calculation involving ionization energies and electron affinity data. The scale that we typically use is the Pauling scale. Okay? It's based upon bond enthalpies, so the energy required to break a bond in various molecules is used to define this electronegativity quantity. It has a range between 0 and 4. Metals have low electronegativities, so they have small values for the Pauling electronegativity, whereas nonmetals have high values of the electronegativity. And so nonmetals tend to pull electrons towards themselves in a molecule, whereas metal-type atoms tend to be more electropositive. Fluorine is the most electronegative atom on the periodic table. It has a value of 4, and all other atoms have smaller electronegativities. So here you can see all of the metals. They have relatively low electronegativities, whereas the nonmetals, they have relatively high electronegativities. Fluorine is the largest, followed by oxygen, followed by nitrogen and chlorine. Okay? So we can think of electronegativity as a periodic trend. Okay, it varies periodically to some extent. It decreases as you go down the periodic table, and it increases as you go across the periodic table. Students will often draw a line pointing from the bottom corner of the periodic table to the top corner of the periodic table to tell them how the electronegativity increases. Fluorine's the most electronegative, and down here cesium and francium, they have very low electronegativities. The concept of electronegativity is used to explain a lot of phenomenon in chemistry, and so this is one that you definitely want to know and be prepared to use both in this course and in your future chemistry courses. So in this example, we are being asked to choose which of these bonds are more polar or less polar. And the way that you can, it turns out so that the larger the electronegativity difference between the atoms which make up the bond, the larger that difference between their electronegativities, the more polar the bond will be. Okay, and so in this example, we're being asked to evaluate the relative polarities of these different bonds. Okay, so we have a pH bond, phosphorus-hydrogen bond, a hydrogen-oxygen bond, and a carbon-chlorine bond. And so what we're going to do is turn back to this periodic table, and we're going to look at the electronegativity differences between the atoms. So for phosphorus, we have a 2.1. For hydrogen, it's 2.1. For oxygen, it's 3.5. For carbon, we have 2.5. And for chlorine, it's 3.0. So looking at the phosphorus-hydrogen molecule, we see that the two atoms have the same electronegativity, which means there's not a big difference between them. So this is a relatively nonpolar bond. The difference between the oxygen and the hydrogen is the largest. And so this is going to be the most polar bond, and this will be intermediate, the carbon-chlorine bond. So ranking these in order, we would say that the hydrogen-oxygen bond is the most polar. Then we have the carbon-chlorine, and then we have the phosphorus-hydrogen bond. Let's do another example. So we'll look at a carbon-oxygen bond, a carbon-sulfur bond, and a hydrogen-bromine bond. So let's look at the electronegativities. So for carbon, it's about 2.5 compared to 3.5 for oxygen, 2.5 for sulfur, 2.5, hydrogen 2.1 compared to bromine 2.8. Okay, so this gives us an electronegativity difference of 1. Here the electronegativity difference is 0. This would be an electronegativity difference of about 0.7. So the carbon-oxygen bond is going to be the most polar, followed by the hydrogen-bromine bond. And then the least polar of these three bonds is going to be the carbon-sulfur bond, because there's not that big of an electronegativity difference between carbon and sulfur. Let's see. Why don't we go ahead and do part C? See if this one makes any sense. We've got carbon-hydrogen, carbon-nitrogen, carbon-oxygen, nitrogen-hydrogen, oxygen-hydrogen, and sulfur-hydrogen. So a lot to compare here. Our hydrogens are 2.1, oxygen 3.5. Nitrogen is large as well, 3.0. Carbon was 2.5. And sulfur 2.5 as well. So the carbon, hydrogen and sulfur hydrogen are about the same. So they have a difference of about 0.4 between them. Here for the carbon nitrogen, we have a difference of about 0.5. 1 for the carbon-oxygen bond. For the nitrogen-hydrogen bond, we've got about 0.9. And for the oxygen-hydrogen, we've got about 1 as well. No, I wrote this down incorrectly. This should be 2.1. And so that should be a difference of about 0.4. So which one's going to be the largest electronegativity difference? The carbon-oxygen, definitely, is going to be the most polar, followed by the nitrogen-hydrogen. Oh, this should actually be 1.4. Yeah, that makes more sense. So really, it's the oxygen-hydrogen bond, which is the most polar, then the carbon-oxygen, then the nitrogen-hydrogen. Then where are we? So we've gotten that one off, this one. We did this one. These guys are about the same. This one is a little bit more polar, so we're going to put the carbon-nitrogen bond, and then we really can't distinguish between the carbon-hydrogen and the sulfur-hydrogen. They're about the same. I'll go ahead and leave part D as an exercise for you guys to try. And I'm going to stop this video here, and we'll pick up in the next one with Lewis structures.